お席にお戻りください。続いての発表に移らせていただきます。ピントンカウンティファンリャオハイスクール。テーマは、Suppression of Shuttle Effect of LIS Batteries by Carbonized Interlayers of Different Temperatures Derived from Barringtonia Leaf です。Are you ready? Please start.
Hello everyone, we are students from Taiwan, Pingtung County Fangliao High School. Our research topic is separation of shuttle effect of lithium sulfur batteries by carbonized inner layer of different temperatures derived from Barringtonia leaf. よろしくお願いします。Barringtonia asiatica are commonly seen along the coast in southern Taiwan. Thus, its leaves can be easily obtained locally. In this study, these leaves are carbonized at high temperatures and are used as an interlayer for lithium sulfur batteries to investigate their effects of separation of shuttle effect. The position of upper and lower epidermis will create different electrochemical results because the subtle differences in the structures of upper and lower epidermis themselves. The interlayer carbonized at 1000 degrees has a better electrochemical effects, which indicates that it can effectively inhibit the generation of shuttle effect. Lithium sulfur batteries are currently a highly promising type of batteries, which has advantages such as higher capacity, higher energy density, and has a lower price than lithium-ion batteries. However, there is a significant issue that affects battery cycle life, known as shuttle effect. In order to mitigate the impact of shuttle effect, we aim to find easily accessible waste material from daily life with simple manufacturing process. Our goal is to promote the reuse of natural resources and respond to environmental protection and sustainable development. Surprisingly, the inconspicuous fallen leaf hold values that we often overlook. Then, what is the shuttle effect? During the discharging process of lithium sulfur batteries, long-chain polysulfides will dissolve into electrolyte and diffuse toward the anode due to concentration and polarity effects. This polysulfide will directly react with lithium, forming low-chain polysulfide, which is the final product after electric discharge. This polysulfide then further corrode the lithium anode and cause the loss of active material, shortening the battery cycle life.
Okay, there is a special detail worth mentioning in the experiment because we cannot visually distinguish between the upper and the lower epidermis after carbonization. Therefore, throughout the entire experimental process, we place the leaf with the upper epidermis facing upward to ensure the correct orientation during the experiment. Originally, the upper epidermis with its natural structure is functioned to keep water in the leaf. But after the upper epidermis is carbonized, now it serves as a locking film to trap migrating polysulfide, and then the trapped polysulfide are absorbed by the micropores and distribute on the carbonized mesophil tissue. So how do we prepare the interlayer? This is our process diagram. First, we clean and soften the leaf, and then kill and dry for 24 hours. Afterwards, we carbonize them at temperatures of 600, 800, and 1000 degrees respectively. After the leaves are carbonized, we cut them into appropriate sizes. And these images are the leaf surface observed through an SEM microscope. We can find that as the carbonization temperature increases, the surface of the leaf gets relatively smooth. As we can see from the images, the impurities on the leaf surface, which is white spots, gradually volatilize and decrease. The lower epidermis also shows a similar trend. By the way, you can also see the thermotype in the image as well. Next, we conducted analysis on battery with interlayer carbonized at different temperatures. Here is a diagram of battery charging and discharging in the first cycle. Firstly, we can observe that the interlayer carbonized at 1000 degrees Celsius performed with a high stability on the discharge plateaus, which indicate the better conductivity of the battery. On the other hand, the performance of the interlayer carbonized at 600 degrees Celsius kept on stably dropping on the discharge plateaus. So, we think that the impurities on the leaf surface may reduce the conductivity of the battery.
In the cycle test, the battery with the interlayer carbonized at 1000 degrees has the highest initial capacity, and its capacity retention rate even reached up to 82.63%, which means the battery cycle life is much longer. In the CV test, the sample interlayer carbonized at 600 degrees shows little degree of overlapping, which also indicates the battery an obvious shadow effect. And on the other hand, the battery with the interlayer carbonized at 1000 degrees exhibits the highest overlapping. It shows the most complete peak shape and almost no polarization phenomenon. A sharper oxidization peak indicates faster reaction kinetics. On the other hand, its larger area suggests a higher capacity of the battery. So we can also say that the influence of the shadow effects is relatively light. From the serial performance analysis, the battery with the interlayer carbonized at 1000 degrees has the highest capacity and the better ability to withstand high current density even after it has just gone through quick charge and switch back to the slow charge. However, the battery with the interlayer carbonized at 1000 degrees and the one carbonized at 1000 degrees inverted and the one carbonized at 600 degrees shows the lowest capacity when set at 0.5 C, which basically indicates the battery had no charging and discharging capability at all, and also had poor conductivity. In the EIS analysis, the battery with the interlayer carbonized at 1000 degrees had the lowest total impedance, decreased by nearly 70%. So let's talk about our conclusion of suppressing the shadow effect. Firstly, the upper epidermis facing the cathode is more effective than the inverted placement of the interlayer. Secondly, the battery with the interlayer carbonized at 1000 degrees performed the best in the every analysis. We speculate that due to fewer impurities on the surface after the carbonization, the upper epidermis can more effectively trap the polysulfide. And then we identify several advantages of adding an interlayer carbonized at 1000 degrees in the lithium-sulfur batteries. That is, we can enhance the battery cycle life in terms of capacity retention, and reduce the total impedance. Also, our study responds to the 7th and the 9th goal on the listing of the SDGs. Our studies helps promote the use of clean energy technologies, lessen dependence on limited resources, also encourage the use of renewable energy. Additionally, through the scientific research and the innovative technologies, we utilize Barringtonia leaf in the lithium-sulfur batteries and supporting the application of new technologies, bringing new possibilities to related industry. This design of the research based on our local materials promote the application of renewable resources, achieving sustainable and environmentally friendly energy production and storage methods. This not only advances eco-friendly technology, but also opens up new possibilities for the application of renewable resources. With technological advancement, these kinds of solutions obtained from local materials will become an important part of future development, bringing positive impact to the environment and energy utilization. As review, when we are selecting the leaves, we pick up 5 kinds of leaf in our school, and we conducted a test, charge and discharge it at the first cycle. And the Barringtonia leaf performed the best, so we keep our research with the Barringtonia leaf. For example, compare the Barringtonia leaf and the Polyquin formosan leaves. We can see that the discharge plateaus of Barringtonia leaf has a high stability, and the discharge plateaus of the Polyquin formosan has a unstably dropping. Also, when we conduct all the analysis, we open our battery and compare the battery with interlayer and without the interlayer. You can see that the yellow materials is the polysulfide come out during the shadow effects. And you can observe that the battery with interlayer, there is no yellow materials at the polysulfide. So we can assure that our interlayer carbonite at 1000 degrees is feasible. これで私のプレゼンを終わります。ご清聴ありがとうございました。
はい、ありがとうございました。それでは審査員の先生方、ご質問、ご意見などいかがでしょうか。鎌形先生、お願いいたします。
Okay, I'm not. I don't have any expertise on this battery things, but my question is: have you ever tried to use other carbon material, for instance, paper or stuff like that, for carbon interlayer making? Because my concern is you are using leaves. Leaves are always containing lots of minerals like inorganic compounds. So probably that might have some problem. So if you use some other pure chemicals like a paper, for instance, for making carbon interlayer, what would be happen?
We have done the literature review before, so we know that many people do a research by the carbonized materials, so we choose the leaf. And the leaf after carbonization, its water molecule and the impurities will reduce. So will decrease. So it will have a clearly micropores to check migrating polysulfide.
Okay, good. Yeah. Other comments on it?
And you mentioned that why not to use the other material like paper or other material. That we have used paper before, but after carbonize, the paper become too crispy, and we cannot cut it into the shape we need and put it into our batteries to doing the research.
Thank you. Very good presentation.
他に先生方いかがでしょうか。よろしいですか。はい。それではここまでとさせていただきます。Thank you very much.